Welcome to this explainer. Okay, so have you ever looked at a massive database or even just a giant messy spreadsheet and wondered, how on earth does a computer take thousands or even millions of chaotic data points and perfectly line them up in a fraction of a second? I mean, it literally feels like absolute magic, right? Well, today we're going to decode exactly how computers pull off this organizational wizardry. And honestly, the best part, we're going to do it using surprisingly relatable, everyday human logic. Seriously, you absolutely do not need to be a programmer or a computer science expert to get this. We are going way back to basics to look at one of the absolute most foundational concepts in all of computing.
Okay, let's dive into this. I want you to picture something for a second. Imagine you walk up to a really messy desk. Sitting right there is a massive, chaotic stack of hundreds of unsorted papers, and they've just got random numbers scrawled all over them. Suddenly, your boss walks in and says, "Hey, I need these perfectly sorted from lowest to highest, right now." Now, if you're a complete beginner to sorting, your brain might just freeze up. You wouldn't just stare at the giant pile and try to swap individual papers around at random, would you? No way. You'd instinctively start breaking that gigantic pile down into smaller, bite-sized stacks, stuff your brain can actually handle. You'd sort a few small piles first and then combine them.
Well, it turns out that this totally intuitive divide-and-conquer paper sorting instinct you just had, that is exactly what computer scientists call merge sort. What's really cool here is how this strips all the mystery away from a fancy technical term like algorithm, because an algorithm is literally just a set of instructions. Merge sort is simply a set of instructions telling the computer to take a massive, overwhelming list of data and just chop it perfectly in half. Then it chops those halves in half, and it does it again and again until it's looking at tiny, perfectly manageable pieces. It sorts those tiny pieces recursively, and then, here comes the magic, it merges them all back together into one perfectly ordered stack. Let's just slow down for a second and walk through the exact mechanics of how a computer actually executes this, step by step. So the really crucial thing to know is that it all happens in 5 distinct phases. First up, we divide. We take our giant list and split it right down the middle into 2 equal halves. Second, we conquer, and that just means we keep splitting things down until we're literally just sorting pairs of numbers. Third, we merge. We take 2 of those sorted little piles and combine them. But how exactly? Well, that is step 4, compare. Imagine you've got 2 small sorted piles of paper sitting in front of you. You look at the top page of the left pile and the top page of the right pile. Whichever number is smaller, you pull it off and place it face down in a new final pile. You just keep doing that, comparing the tops of the 2 piles until both of them are completely empty. And finally, step 4, you finish. You reconstruct the entire array by continuing that exact merge process all the way back up to the top.
And this brilliantly illustrates the true genius of the conquer phase. By focusing on 2 entirely separate, manageable piles, we can really see why this method works so well. The computer isn't looking at the whole chaotic mess all at once. No, it completely isolates the left half of the data from the right half. If the computer is currently sorting the left side, it literally ignores the right side for the moment. It brings this incredible, laser-like focus to the task. It takes what looks like an overwhelmingly complex problem and turns it into a series of incredibly simple, binary choices. Left or right? Which one's smaller? Boom, next.
Now, if you ever hang around software engineers, you might hear them throw around this incredibly intimidating piece of jargon, O(n log n) complexity. It sounds like some kind of advanced calculus, right? But let's translate this into plain English for a beginner. In computer science, this term is basically just a grade on a report card. It tells us how fast an algorithm runs as the pile of data gets bigger and bigger. So what O(n log n) simply means is that the merge sort process performs consistently and steadily. It doesn't panic. Whether you give it 10 sheets of paper, 1,000 sheets, or 10 million sheets, the time it takes grows at a very predictable, smooth rate. It's not going to suddenly crash or take a million years just because the pile got a little larger. It is absolutely the ultimate reliable worker.
So let's see how this translates into real-world decisions. Because this algorithm is so insanely reliable, there are very specific times when it absolutely outshines everything else out there. We use it for large data sets because, as we just learned, it doesn't panic under pressure. We use it for things called linked lists and external sorting. But the absolute most important concept for a beginner here is that first point, stable sorting. What does stable actually mean? Well, imagine you have a list of people sorted by their age, but now you want to sort them by their first name. A stable sort guarantees that if 2 people have the exact same name, say 2 Johns, the John who was originally older will still appear before the younger John. It respects the original order of ties. And let me tell you, that is a massive advantage when you're organizing complex data. Let's zoom out to the big picture for a second to really grasp the sheer power and scale of where this is used in our everyday digital infrastructure. You might be sitting there wondering, okay, why does this matter to me? Well, every single time you search through massive database systems to look up an online order, merge sort is very often the invisible engine keeping all those records in perfect order. When data is simply too massive to fit into a computer's active memory, think of giant external storage drives on big servers, merge sort handles that data on the disk super efficiently. It is heavily baked into standard programming libraries. Basically, our entire digital world relies on this precise, predictable human logic to keep modern life functioning without lag or errors.
But just between us, there is a catch. And it is arguably the biggest logical trap that coders fall into when they're first trying to understand how all this works. We call it the extra space assumption. Let's go back to our messy desk analogy for a minute. If you take one giant pile of papers and start splitting it into 2 piles, and then 4 piles, and then 8 piles, what happens? You need a lot more desk space. You can't just do this trick in midair. In computing, that desk space is memory. Merge sort requires additional temporary memory space, specifically what tech folks call ON memory, to hold all those newly divided halves before they finally get merged back together. If you forget to allocate that extra space, the whole system just grinds to a complete halt. And honestly, that's not the only pitfall out there. When computers actually execute this, they have to be meticulously careful about the details. A really common mistake is an uneven split, meaning the computer doesn't chop the pile exactly in half, which leads to lopsided piles that completely confuse the system. Another huge one is forgetting the merge step logic, specifically not copying the remaining elements. Remember earlier when we were comparing the top pages of our 2 piles? What happens when one pile runs out of pages before the other one does? You have to remember to scoop up the leftover pages from that unfinished pile and add them to the bottom of your final stack. If you miss even one single leftover piece of paper, you completely break the perfectly sorted order.
Ultimately, the core goal of merge sort is beautifully summarized by this simple idea: to achieve efficient and stable sorting with predictable performance. It is truly marvelous to think about how such simple human logic, just dividing a big, scary problem into smaller, manageable pieces and patiently comparing them, powers the most massive and complex computing tasks on Earth. It literally brings order to chaos. It makes the unpredictable completely predictable. And it leaves us with a pretty provocative thought. If computers use this highly reliable step-by-step strategy to perfectly organize millions of chaotic data points without ever panicking, how might you apply this exact same divide and conquer stability to organize the overwhelming tasks in your own life? Thank you so much for exploring this fascinating concept with me, and I will see you in the next explainer.